Okay, good morning, bom dia. So let me finish the presentation we were doing last time. So we saw, um, let me call this a computing derivatives in a non-standard fashion. So method one was by Squire and Trapp. Which is the we call it the complex step method, right? We saw how this worked last time. So we approximate derivative of a real value, right? F of x by complexifying it, taking a complex step, and so on. And we saw this, at first to me, non-intuitive formula, this imaginary, that what we're really doing here is we're computing the y derivative instead of the x derivative of our original function, it's the y derivative of the harmonic conjugate. Okay? And then the one I did, which is the Hilbert transform scheme, which uses this identity. Okay, so if you remember this identity, this is basically the Hilbert transform minus. The Hilbert transform is the inverse, so minus Hilbert transform, a Hilbert transform gives you back the function, but since here I'm using the Hilbert transform of the derivative, the Hilbert transform of the Hilbert transform of the derivative gives us the derivative with a minus I. So I used this, and basically we put together these two guys with the alternate trapezoid rule, okay? This is, of course, expensive at the time being, but when I sort of discovered this, I had a lot of fun because it was like out of the blue in the sense, what does out of the blue means? Doesn't use Taylor series, doesn't use a basis of a function like spectral methods use, right? They use a basis, Fourier basis, Chebyshev, or whatever, okay? And this is, so therefore this is spectrally accurate, okay? And this one is very good when h goes to 0, very small h, okay? So let's see if I can make this paging work. Okay, good. Not having full control, a little fast, but so the alternate trapezoidal rule ends up being a method that uses the integration of the second derivative of the function. And these are basically multi-resolution stencils of the second derivative. So what do I mean? Let me come back here. This operator here, the discrete operator, is f of j minus 1 minus 2f to j plus 2, oops, plus divided by h squared, okay, but with different resolutions. Okay, so I think I put an L here. Let me put an L here. L minus L plus L, and the spacing LH squared, where L is 1, 3, 5, up to the number we can do on the grid. Okay? So it's all these spacing. It does some sort of a weird averaging of all these terms. So this is with 1 spacing, 3 spacing, 5 spacing, and at the end we got the derivative. Okay? So what I didn't show to you last time, I will quickly review last time just so we can log in, is I didn't compare this guy with this guy. I showed you the result of this guy compared with central difference for the first derivative, and this guy won the competition for very small h. So when h became very, 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 very small, the finite difference just gave 0. It couldn't see. There was a cancellation error. And this guy gave like many digits of accuracy. Now I'm going to compare this guy with this guy, and in particular this guy with an h, which is not that small. And this guy's going to win the competition. But it loses in the sense of efficiency. It's expensive. But in terms of accuracy, it wins the competition. So let's see how that goes. Okay, these are the theorems, and then I did this on purpose, a good point to explain to you what is Richardson extrapolation. So you know in your minds Richardson extrapolation. You don't even have to remember the formula, whatever. It's just that you use the same method on 2 different grids, and if you do things right, you can cancel first order terms and get a higher order method. Okay? As everything in life, it's a little more work. You pay more, but you get a better product, right? So. Right. Whoops, what am I doing? I think, yeah. I was doing the wrong movement. So these are the differentiation matrices. I'm not going to get into this. Well, we saw these results. Now remember, the dots are the error for FFT, and the blue is for the distributional finite difference, which is the one, the Hilbert transform I'm calling like this, distributional finite difference. This is for other Fourier modes. We saw this one too, that, right, the error of the finite difference depends on the location of the maximums and so on. We saw this also. Here's for the Gaussian. Okay, so I'll have to go up in just a second. So here's the thing. No, you won't be able to understand this. I think I have to go back up. It's because the figures are coming after the text. Oh, here it is. Oops. Well, I'm not having very good control with this. Isso aqui está funcionando ou não? Deixa eu ver aqui. Okay, so now to do a competition with Squire and Trapp, they studied this function. Is that correct? Yeah. Yeah. 9.5. So this function is not periodic. My method is periodic, right? Because I'm using the periodic Hilbert transform. So what I did is, okay, I shifted this point to the middle of my interval, my 2 pi interval, no big deal, right? But this function still is not periodic. But I want to check, so this is what I did. I want to check the derivative only at one point. The derivative is a local thing, right? So only at one point. So I put this point in the middle of my interval. And because I just want to check the derivative at that point, I multiplied this function but by what's called the super Gaussian. So why is that? Because a super Gaussian, I'll show you the picture. That's the picture I showed, and then I come back to that. No, let me explain. Super Gaussian is basically a Gaussian to some power. Okay, I'll show you the formula. And what that makes, the super Gaussian, so I'm going to use basically, is it there? Yeah, it's there, but one cannot actually see. Yeah, so I'm going to call S little s g of x my super Gaussian, which is basically the Gaussian to some power. Right? The formula is it's not good to see, but what this does, the super Gaussian basically has a graph like this. Okay? And I can control this width. Okay? So what I do then is if I multiply the super Gaussian by this function, and in particular this point is over here, okay? Since this is 1, whoops, let me put it close. Right? Since it's 1, the derivative at this point remains the same, right? But I'm doing a smooth cutoff of this function, right? I could do that with hyperbolic tangent, whatever. I use the super Gaussian, okay? So it's basically a smooth C infinity cutoff where I can control the width, okay? And by doing a smooth cutoff, it's going to be 0 here, and I can do a periodic extension of it, and that's no big deal. Because I only want to compute the derivative at the central point where the value does not change, okay? So that's all. Okay, so then, let me go over here, which is, just want to change a little bit. Yeah, so let me write the super Gaussian for you because you can't see it over there. Okay, so I played with different values of gamma, different values of S. And then, with just a few points, let me go back to, so here are the results. I hope you can see on the board, yes. So the exact derivative, okay, let me help reading it for you. The resolution is good, but not so. So the exact derivative, value of the derivative, that point is this one, okay, computed through MATLAB, 18 digits. And then the approximate value computed by the distribution finite difference method with 257 points has all these values. So basically 14 digits of accuracy. Only these last two. For Squire and Trap, okay, if I use the same resolution, okay, I get only just 4 digits of accuracy. And this is with the, oh no, this is for just centered finite difference, and this is the complex step method. I only get 4 points. So I will get 14 digits of accuracy with the complex step method only if I use 10 to the minus 7, a very small step. And with the Hilbert transform, I get basically the same result with just 10 to the minus 2. Okay? So computing the derivative where the exact value is up here. So, so this is was very nice, but I have to say the truth that the method I use is very expensive. It takes much more time, right? So I have to improve that. That's one thing. I have ideas, but I haven't yet done that. And now let me show you the graphs. So since now I showed you the results, let me show you the graphs. So here's the one super Gaussian. This is the curve I'm trying to approximate the derivative. Okay, so you can see here in the middle of my domain, which is pi x equal to pi, both curves match, and we get the right derivative. This is the super Gaussian, and then I use the super Gaussian just for fun. I use the super Gaussian. Now what am I doing here? Oh, I checked with 2 different super Gaussians. So you see, this one is more a faster one. This one is another one, and you know the results were pretty good. This is not such an interesting graph. Yeah, just to show that actually it worked very well. You see, this super Gaussian here, if you can see the mouse, this super Gaussian here is a very wide one. I can make one that's more local, okay? I can make one more local. So now I remember what I should mention is that, so these are with different parameters for the super Gaussian, and this also worked very well. If I make it too narrow, at one point is not as good, right? But this shows that, and this is one thing I haven't figured out in an efficient way, is that this shows that if I use just a few points near my point of interest, which is x equal to pi, the formula works very well. So it's not that I have to use, you see, it's something that, this, for example, are things I cannot mention to students who are still taking calculus, which is not your case, right? Which is derivative of something local. And actually I'm using something non-local, an integral, to compute the derivative. So that would mix up, right? Students that are learning that to differentiate and to integrate, and then you integrate to differentiate. It's not the right way of saying things, right? And then the things that if I make this sort of integration a little more local, I still get good results. I still yet do not fully understand, have ideas of how to make this integration with like a cutoff function more local, because then I can gain in terms of efficiency, because I don't need all the points. Of course, right, I just use the closer points to get this high accuracy. That I still don't fully understand. I have ideas and so on. So anyway, interesting stuff, but to be understood. Okay. So this finishes this, and then I want to mention our last sort of example of numerics, well, which is another paper. Well, you will see how understanding the PDEs, right? The simple PDEs. I'm going to show you the acoustic problem, right? The linear system of hyperbolic problems, of hyperbolic equations. We're playing with the mathematics, you know, knowing the PDEs, tricks in PDEs, you can get better numerical methods for certain situations. Okay, so that's the goal of our last example. Ele não tá gostando, não está querendo abrir. Não sei porquê. É um PDF. Deixa eu ver, será que tem que a gente abrir de novo aqui? A gente vai ter testado antes. Não sei se ele está com esse negócio na frente no nome. Vamos botar. Porque não deveria ter isso. Eu baixei ele como os outros, então. É aqui, André, bibliografia.
Isso aqui? Estão todos com...
Ah, todos pego de baixo, é isso. É isso. Eu apontei. Não sei porque aparecia aquele outro com aquele pontinho estranho. Obrigado. Você tirar aqui o negócio, não? Tá bom. Okay, so maybe let me start on the blackboard, this one. So look, obrigado. So this is what we're going to do. So remember that we had this acoustic problem like this. Okay, this is z direction, and this is the equation. So this is the acoustic waves in the layered medium. Okay? And I want to show you a smart way. The smart way we sort of solved this problem. This was with a former student. Two former students. One was actually scientific initiation. One was a PhD student. Let me put the reference. So this is a paper with Alfaro, Correia, and myself. We called it Complete. So the title explains what we're trying to do. And it was a lot of fun. Time reversed refocusing in reflection with an acoustic Lagrangian model. So this is paper 2007. Okay, and some of you have seen this in a little bit of what I'm going to write quickly in the PDE's course. So the speed which is basically the eigenvalues, is the square root of these two guys. The impedance is also the square root of these two guys, but just in another way. So the impedance has to do with reflection. Do you remember what this is? Let's see if you remember what this is. Do you remember what this x is? I mentioned this in this course, but I also mentioned this in the PDE's course. So 1 over the speed 1 over the speed, usually it's called the slowness, at least in acoustics, right, in geophysics. And this is basically the travel time. Okay, so I'm doing a very quick review of the PDE stuff to show you how I'm going to use this for the numerical method. So this is the travel time. Remember the units, this is speed, it's distance over time. So this is time over distance, times distance, so it's the units of time, okay? And then, if we change variables, so now we can call this the down mode, and write it to a change of variables like this. You don't have to check this, it's just for completeness. I mean, you don't really need to understand all this change of variables in terms of understanding the numerical method, but this. And this is the upgoing mode. Okay, so right, P is pressure, U is speed, this is wave speed. Okay, and then if I do this change of variables, we get the following system. Okay, so this is basically just rewriting quickly, change of variables, things of PDEs, of this system of PDEs, which we've seen in some courses. Here I think I showed it before quickly, but the essence in words is this. I have this system here for pressure and speed. So think of these, right, as I mentioned. This is a layered medium, right? The speed is constant in each of these mediums. You have this pressure wave traveling, right? This is like a geophysical problem. And then you do this change of variables. You call D the downgoing mode. And U the upgoing mode, right? Basic reflections. Or if you're thinking of acoustics, it's like the echo coming back. Okay? And then if you do this change of variables using the impedance, blah, 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 how do I know? And this is the way to confirm that this is a downgoing mode and this is an upgoing mode, because look at this. These are basically the characteristics, right? This is one direction, this in the other direction. This is a wave moving in one direction, this is a wave moving in another direction, right? So if I change, so I can make a total derivative of this, and then D is on one characteristics, and U is on the other one. If, and here, they are coupled due to the reflectivity, due to the fact that we have a heterogeneous medium. So this is like a logarithmic derivative of square root of zeta. If zeta is constant, that means the medium doesn't change. This guy is 0, and these guys are decoupled. So then the idea for the numerical method is going to be here in the next page. Right? Note that with this change of variables here, right, if you have D and U, you can solve the system for U and P and recover your original physical variables. Right? If you solve for D and U, then you just solve the system in U and P, and you recover our physical variables. But we're going to solve the problem numerically for D and U. So note two things that are nice for numerics. So now we're back to our numerical course. So we have this system of PDEs, which by tricks from PDEs, we rewrite like this. Okay? Now note the following. If there's this guy's constant, these two guys don't talk, and they will be constant along these characteristics. Okay? The other thing is that the characteristics here, by using travel time and time, these characteristics here have been normalized to plus or minus 1. Note that here, the velocity is z-dependent, depends on where you are. And with this change of variables, the speed does not depend on where you are. It's constant. So that means we can write our numerical method like this. And this is a schematic. So I'm going to do, so we can do basically a Lagrangian scheme, which is our grid, is basically this yellow grid. So the PDE system is centered at j minus a half and plus a half, this node here. Okay, so the PDE is centered at this node, but our variables, our discrete variables, they live on these nodes here. Okay, that's the trick I mentioned already too. Sometimes we can think of things centered at a point outside the grid. Okay, so look at this. So then the numerical method I can write like this. And let's say that h is equal to delta x and is equal to delta t, because we have normalized the speed, right? It's plus or minus 1, right? The characteristics. So okay, so this equation that looked like it's a partial differential system. When we're solving it along characteristics, it looks a bit like an ODE, right? Just one derivative here. And look at this derivative here. It's a Lagrangian method over a characteristic. So this guy here, which is the downgoing guy, it's on which characteristic? I'm going to have the J minus the J the j at time plus 1 minus this guy. So it's this characteristics here. So this is on the C plus characteristic, which is this one. Let me call this one C minus. Let's see if I have the, yeah. Okay. And then this guy here is on the C minus characteristic. So it's, which is this one, it's j minus 1, n plus 1, jn, because things are flowing this way, and here things are flowing that way, right? And then, since this term here has to be evaluated at this midpoint, right, it takes an average, and it takes an average, okay? And this method then, with skipping some of the details, this method worked very well for this problem. And I'm going to show you now computational result without giving the details. Right now, it's a little bit, in these last lectures, it's showing recent sort of research topics using numerical PDEs. Okay? So basically, the take-home message for you, right, without seeing all the details, maybe not fully understand because just skipping things, that we rewrote the original PDE system, which is in space and time, where z is going that way, so it's down, okay? So here, sorry, down would be going this way, and up is going this way, so this is going in the positive direction of travel time, right, because it's traveling down, whoop, okay? And that complicated system with a variable coefficient now has been written like this, with plus or minus characteristics. And look, if I don't have this guy here, right, all I have to do is assign this value here over here, which, look at this, which means dj n plus 1, dj n plus 1 is equal to dj minus 1 at the previous time, because this guy is flowing constant along the characteristics. Right? And now, one of the main reasons, maybe that, not the only one, but one of the important reasons why we used this method is because of this. We did our computational domain like this. Here we have all the layers, very long. You're going to see why, because we're going to do a very nice time reversal simulation. And then, this is our computational domain. And then here, we put let me put here. Here the reflectivity is 0, and here the reflectivity is 0. So, and this is reflectivity different from 0. Do you see what I'm doing? Let me say it in other words. See if you understand. I'm going to put my heterogeneous medium embedded in a homogeneous medium for boundary conditions, as I will explain to you just now. So I have the heterogeneous medium where things are going boom, crazy dynamics, back and forth, back and forth, back and forth, right? Why back and forth? Because of this. So the U affects the D affects the U, so there's the reverberation, okay? But once it reaches near the boundary of my computational domain, I make the medium homogeneous so that these two guys decouple, right? Because if the medium is homogeneous, R is 0, these two guys decouple. And then I have a very good here radiation condition, and here I have another very good, this is for U and this is for D. So basically I allow information to flow out of my computational domain at the, well, for you is at the right and at the left in a nice way, because U and D do not talk to each other, okay? This is what so I got here a very good, very nice and simple radiation condition. So here I'm forced to mention to you another name important topic in numerical PDEs for you to keep in your heads and take home, which there are people who are experts on this, which is on developing radiation, sometimes it's called radiation, or absorbing boundary conditions. Does the name explain things to you? Of course I'm going to explain, but just to check, does the name explain to you already what's going on? See, you have a solution which is not periodic, so the wave is going to come. What happens when it hits the boundary of your computational domain? Actually, what I'm going to do here is, the theory I'm going to use here is that I know that if this medium, half-space medium, is infinite, random medium, I'm going to check that localization, Henderson localization thing I mentioned to you, that everything comes back. Remember I mentioned this last class. Everything comes back, okay? But I cannot do an infinite medium numerically. So I'm going to do a medium which is big enough so that I get effectively the same behavior as if it was infinite. And as the wave reaches this end of the domain, I don't want it to, say, for example, reflect back and come back in. I want it to go away and keep on going. So there are techniques in numerical PDEs which are called radiation boundary conditions, which are conditions that allow the information to radiate, to go out of your computational domain without generating any, say, spurious reflection. There's other technologies which are called absorbing boundary conditions, which is also not a technology, depends on the PDEs, where people develop here a boundary condition that's a little bit like a damper, like an airbag, right? The solution comes out, and it sort of somehow is, quote unquote, absorbed there, right? It's a little bit like a radiation condition, and nothing comes back, okay? And there's also names like matched boundary conditions where you match with things. They're all more or less part of the same category of numerical strategies, which is strategies at the boundary so it does not make things come back in a spurious way. Here, for this problem, it was we saw we could use the most simple, ridiculously simple radiation boundary condition, which is that here, in this region here, dn plus 1j is equal to dn minus 1n. Or maybe we should, yeah, that's right. Okay, so at this point here, this guy receives the information from the node right here next to it in the previous time, and I record that, and that's it. And at this node, u j minus 1 n plus 1 is equal to uj n, right? Because this is 0, boom. Look what this does. The wave that's coming this way, which is the u, right? At this point here, it will be equal, at this point here in the next time, it will be equal to this guy here at the previous time. But at time 0, there was nothing there because the wave was coming this way. So this keeps nothing coming in here. So these are very good. These are very good. This condition is a radiation condition, and this condition is a non-reflecting condition because nothing comes in. Is that clear? Right? Just think of this as at time 1. At time 1, at this node here, at time 1, which is n equal to 0, it's going to be equal to the initial condition here, which was 0. So nothing happens. So it keeps on going that way because I'm never going to have anything coming in from that direction. So these two conditions work very well. And now I'm going to show you the numerical results, okay? So the numerical results is that fantastic simulation or a phenomena, I would say, not simulation, of time reversal, okay? So what is time reversal? I'm going to put a wave here, which is going to come in, and it's going to interact with this random medium. And as we saw before, so this is r different from 0, the wave is going to be smaller, and it's going to have, this wave is coming this way, and this guy here is multiple scattering. It's going both ways, okay? And then this reflection eventually reaches here, and it's coming out. I'll just record it, and that's it. Then I'm going to get the signal that was recorded here, and I'm going to send it back in to the same medium, and according to a theory by Jean-Pierre Fouque and Clouet and some other people, this crazy signal will reorganize itself and generate a copy, a small copy of this pulse that I've already shown to you. But now, because of these conditions here, I can make this medium very big, and I'm going to show you that actually I'm going to get this crazy signal and reconstruct the exact initial condition. And this is because this method is very nice, worked very well, and is conservative, right? There's no dissipation or anything. So let me show you the results now. So let me go here so I can have better control of the paging. So, okay, so here's our random medium. This is some technicalities and so on, our numerical method. Okay, so here's like the simulation looks like. Okay, you see, right, the wave, the recorded signal, and I'm going to send the recorded signal back in. So this is the first, so let me go here to help you. This is the very first simulation, okay? And actually, I should mention something, sorry. The initial pulse in this case, so here's my domain, right, the random domain. And instead of using a Gaussian, the initial pulse is a derivative of a Gaussian. Okay? So this is the derivative. So it's the Gaussian. So it's d dx a Gaussian. Okay, derivative of a Gaussian. So look at this. Here's the derivative of the Gaussian. And my domain is so long. It's about 400 Gaussian widths long. Okay? So we can barely see the Gaussian here, no problem. But now you can see the Gaussian. So after it traveled, say, 120, look at here, the apparent diffusion, right? The pulse is wider and smaller. And a lot of the energy from this pulse here has been converted to this crazy disordered tail. And the tail is coming out of my domain, but because of that radiation boundary condition, I'm recording everything that's coming out. Okay, and the pulse keeps on going, becomes even smaller. There's more radiation. Here you can barely see the pulse, and here there's really just a little bit of energy. A little bit of it is coming out to the right, and so on. Now in the second simulation, we're going to get this crazy signal here, okay, that was recorded outside this border, and I'm going to send it back in, okay? And watch this. This was a lot of fun doing. Watch this. In this crazy signal here, when I send it back in, I'm going to get a copy of my initial data. Just by sending it back in. That's a time reversal refocusing. Let's watch it. Oh, the other graph I don't have. So here's already the zoom. So here's the graph of what came back. Okay, the initial data, and this is different times of recording. I get back the exact same pulse. Okay? By sending back that crazy signal, which we don't have for space reasons. I present this usually when I give talks, but not in this paper. We don't have that graph, which is basically sending this guy here back in. It generates the same the same pulse. And now, as a last experiment, these are other things showing, I mean, I'm not going to show it now. Now look at this one. Look at this one. In this one, what we did is this. Instead of sending one pulse like this, we sent a train of pulses, like say this, then the space, this, like that. Okay? There's a sequence of pulses or empty slots, and we're sending all this into the random, the disordered medium. Okay? Is it clear? Instead of sending one pulse, I'm sending several pulses, like pretending it's like a bit stream, right? Like a 1, 1, 0, 1, 1. Okay, but not with solitary waves. It's not optics. This is just for the fun of waves into this random medium. Okay, is that clear? Okay, so here it is, right? I have this stream of pulses, 1, 2, whatever. I think there's like 2, 2, and what. Anyway, this is the initial signal, and this is what came back. Okay, this crazy, disordered signal came back from the reflection of these guys over here, over the random medium. Okay, the randomly layered medium. So then we record this signal here, this crazy long signal. We record this signal and we do time reversal, which is whatever was recorded last, like this part, will go in first. So it's like solving the same PDE system, where now the initial data is this dirty signal moving backwards. Okay? This is very simple to do. Basically, many of you would know this. So whatever came back through, let's say, through the left-going characteristics, okay, so whatever came back through the left-going characteristics, once I do the next simulation, I'm going to get this information, and I'm going to put it on the right-going characteristics so that it comes back into the medium. And look what happens. This is then what comes out. So the reflection of the reflection is this guy. Okay, so it's a copy of the exact thing. So this is non-intuitive. Mathematically, I kind of understand, but not intuitive. This crazy signal here has information from the initial data, has information from the medium, that is the coefficients of the PDE, and if I send this back in the right way, it reorganizes itself through reflection, and what comes back through the left-going characteristics, the C minus, in the second simulation, is this, a copy of that. So this generated this, and this will generate this. So quite amazing that this dirty, crazy signal interacting with a crazy medium, it has to be the same medium, reorganizes itself and produces the same guy. And Daniel, in his thesis, one of the things he showed in his thesis is that if you perturb a little bit the medium, the coefficients, after you did the first simulation, you still get some, it's quite robust. You still get some reasonable refocus and so on. It's not, of course, as clean and so on. There's issues, but this refocusing phenomenon is quite robust. Okay? So this is something that worked very well numerically, right? So first, that we had these radiation conditions. Why it was important for us? It was important for us so that we could record what was coming out of our domain for a very long time. If I didn't have these radiation conditions and I asked you to do this simulation, what would you be forced to do? If you wanted to put a very big heterogeneous medium, disordered medium, what would be, if we didn't have a good radiation condition, what would be one way of doing the same simulation? Let me give you a hint and see if you agree. I would need a computational domain 3 times bigger than the one I used. Why 3 times bigger? Say it, even if you say it wrong. Look, I'm holding my hands here of where the heterogeneity is, where the disordered coefficients are, okay? This hand here is where the wave is going to come in, right? This hand here now shaking is where I need it to radiate whatever is being transmitted, right? And I have to wait a long time. Look, I have to wait a long time for the wave that came from here. It started interacting, and it's going to come out here. But I need, if it's going to generate a reflection here, right, before it comes out, I need to give time for this reflection here, this information that was produced here, to bounce back and forth and come out here, so I can record the reflection coefficient with information of the whole medium, right? So I have to do a very long time computation because I have to wait for the information to come up to here, so the wave has explored this more far region of my medium, and then I have to wait time for this information that was generated here to have enough time to come back here. And meanwhile, I'm recording everything that's coming out here, okay? So if I don't have a good radiation condition, I need my domain out here to be huge so I can see everything that's coming out, right? And I need my domain here also to be huge so that everything that comes out does not hit the boundary, come back in. So it has to be at least 3 times, if not more, larger than this. This experiment, this simulation here, the computational domain was basically the size of the random medium, just with a little tiny bit of a homogeneous part, just so that the guys decouple. Okay? But if not, I would have to have a domain very long in time and very long in space for whatever was generated. And looked at whatever the information that came from the last moment here to come back was relevant so that it could get exactly the shape. But of course, the energy generated here at the end, the wave already lost a lot of energy. So you can see that this signal is decaying, look, right? Because the last one that came in was already when the signal was already very weak, but because it already had released energy for what's coming back, right? It's weak, but relevant, right? It's small, but not negligible, and it played the role in the previous simulation to recover the full initial condition. So, you see, using the mathematics of PDEs to rewrite the problem before you do the computations was very important. And basically, as the last thing I'm going to say in the course is maybe the first thing I said in the course. Mathematical modeling, right? Understanding PDE theory, then doing mathematical modeling, which is sometimes rewriting your PDE system or simplifying your PDE system, and then understanding what is the best fit in terms of numerical method for that problem, because you understand the properties of the PDE problem that you want to capture numerically. These 3 things are very important, are a lot of fun, and it's basically part of my daily work, right? Sometimes one more than other. Sometimes there are papers which are just the asymptotic reduced modeling of the PDE, right, as you've seen. Sometimes there's papers which is just numerical stuff. Sometimes there's paper which is both. Sometimes there's paper where the numerical stuff is because there's some new numerical ingredients. Sometimes the numerical part is because you want to infer, provide evidence of properties of the PDEs where you can't prove things, but you can, with careful numerics, provide information of the numerical properties of the PDEs, and sometimes, which is even better, which is the end of the underlying physics, right? So that's basically the story, right? And here, basically, we are finishing the course, right? And these last lectures with papers related to my students on is to show how all these things come together, right? And in the numerical methods course in PDEs, right, the sky's the limit. There's many things I didn't talk about, right? There's many things actually which, first, I'm not an expert. Other things that I know I could talk about. But the important thing, I think, in a course, in particular in a graduate course, is for us to learn how to learn, right? Because I'm still a student until now, right? I'm old, but I'm a student because I deal with many problems I don't know. I have to study like this bouncing droplet problems with deals with quantum mechanics. I didn't know anything of quantum mechanics 10 years ago, and I learned a little bit. So we have, the course is for us to learn how to learn, and therefore, that's what all the things we do here, from simulations to reading text to writing reports, is for us to learn how to learn. So that's the goal. So I'll finish here. Obrigado.